All right, so we talk about block ciphers, and now we are considering mode of operation. So before moving on to following slides, I will also use some notation. Actually, I will give some like a mathematical definition, but I will also show pictures, so it will be easier to understand from the pictures. But let's also see the definitions in the following notation. So N will be the total number of plaintext blocks. K will be the secret key. MI or sometimes PI will be the ith plaintext block. CI will be the ith ciphertext block. ENC will represent encryption, and DEC will represent decryption. And IV will stand for initialization vector. So before moving on, maybe we should first describe what an initialization vector is and what the nonce is. And sometimes these are actually used interchangeably, but the main definitions are different. But sometimes instead of nonce, people say IV and so on. So initialization vector, IV, is an input to a cryptographic primitive like block ciphers, hash functions, message authentication codes, etc. Okay. So it comes in many different algorithms. And cryptographic nonce is an arbitrary number that may only be used once. This is important. So you cannot use a nonce twice. Okay. There are some sentences like, you cannot return to home twice, or you cannot, bathe in the same river twice. So you cannot use the same nonce twice. Okay, just think about it like that. Important thing is that nonces and IVs should be generated randomly. Okay. Most importantly, most of the time, it depends on the scenario. Actually, sometimes nonces are public, sometimes secret, and sometimes IVs are public and sometimes are secret. And sometimes, IVs are fixed, so it is okay to use the same IV. But in some protocols or scenarios, using the same IV might cause a problem, and we call it IV reuse. Okay. For instance, in a few months ago, there was an attack to Samsung mobile phones, where using the same IV caused problems which allowed you to capture the secret keys and so on. So this is why, I cannot generalize IVs and nonces, but just think IV as something that is used when you are starting a cryptographic primitive. When you are at the beginning of the process, you need a random value. So this is called IV. And nonce is sometimes you just generate during that time and you have to use it only once. Okay. Again, in some protocols, these are interchangeable. So, but just think that they should be randomly generated, and sometimes they have to be kept secret, and sometimes they shouldn't be used twice. Okay. So there are a lot of mode of operations, but NIST actually mentions only a few of them. In the 2001 version of the document NIST 838A, it suggests following mode of operations. And in 2010, there was an addition, XTS, because this was a full disk encryption and many other standards. And this is added as a new document. So NIST actually mentions only following this, the 6 operations. So I will only focus on them, but there are more. If you're interested, you can look at them. But although electronic codebook is included in the NIST document, again, it is not secure. So this is why sometimes people don't understand this. So they see it in the NIST document. So they think that they're allowed to choose any one of these from this document, and they choose ECB. But ECB, again, it should not be used for cryptographic purposes. So you can choose any of these. So the question is which one you should choose. Actual choice of the mode of operation affects the security, but also the performance. So you have to choose depending on the scenario. Okay, so let's look at the electronic codebook. So ECB mode encrypts every plaintext block independently. So for every block, you encrypt a plaintext block with the secret key and obtain ciphertext block. And for that ciphertext block, you decrypt it with the secret key and obtain the message block, plaintext block. So as a picture, the encryption is as follows. So you divide your plaintext into blocks and encrypt it with the same secret key independently. And in the decryption part, the person you're communicating with obtains the ciphertexts, write them here, and now they perform the decryption. Okay, so this means that if you are putting this in a hardware, you have to implement both encryption and decryption. This is why I'm actually showing this with different colors. Okay, because in some of the mode of operations, we will see that the decryption will be identical to encryption. Okay, so this has a lot of advantages because it is parallelizable. A block can be encrypted without waiting the encryption of other blocks. As you can see from the picture, you can encrypt Pn without waiting for the encryption of the previous ones, right? It also has random access. A block can be decrypted without waiting the decryption of other blocks, because again, you decrypt independently. Error propagation is limited to a block. This means that if a single bit of a block is flipped due to a transmission error, it does not affect other blocks. So this means that here you perform the encryption, so you obtain the ciphertext and you transmit it, but there was a problem during the transmission, and assume that one bit of C2 block is changed. So the person who wants to decrypt has a wrong ciphertext, one bit is flipped, but even if one bit is flipped, when you decrypt it, the whole plaintext block will be different. Most probably, half of the bits will be different than the original plaintext. But this error does not affect the others. Okay, this is a good thing. But of course, we already mentioned that you cannot use ECB because it has the following disadvantages. Identical plaintext blocks are encrypted to identical ciphertext blocks. So this is unacceptable, and this is why you cannot use it in practice. Also, these mode of operation do not have self-synchronization. This means that if some ciphertext bits are dropped, this synchronization cannot be achieved. This is valid for actually all of the mode of operations I'm going to talk today. So self-synchronization is somewhat important, and this is the thing that we are going to talk about when we mention stream ciphers and so on. Okay, so self-synchronization will not be provided by all of these mode of operations I'm going to talk about. This means that if some of the blocks are dropped, you wouldn't notice it, right? This is the main problem. All right, so we said that one of the solutions to ECB could be CBC, cipher block chaining. So it is defined as follows. Before encryption, every plaintext block is XORed with the previous ciphertext block. As you can see, when you want to encrypt MI, you XOR it with CI-1, then perform the encryption. Of course, at the first block, there isn't ciphertext 0, so you XOR it with IV. So we XOR the first block, first plaintext block with an IV, and the person who wants to decrypt this performs this following operations. Okay, so the picture is as follows. You have the plaintext block 0. You XOR it with IV, encrypt it, and obtain the ciphertext block, but you also XOR it with P1, and so on. So it is a serialized mode of encryption. And the decryption picture is as follows. You have the ciphertext, you decrypt it, and then at the end, XOR it with IV. But I will mention it in the following slides, but as you can see, the encryption is not parallelizable. You cannot encrypt P2 without the encryption of P1 and P0. But in this scenario, actually, the decryption is parallelizable because the XOR operation here is at the beginning and here it is at the end. So you can actually perform this decryption without waiting to perform these decryptions. So you can decrypt C2, obtain this value. Now you have to XOR it with C1, but you already have C1. So you can actually decrypt this plain ciphertext block without decrypting any other. So this is a good thing. So advantages, error propagation is limited to 2 blocks because, you know, if C1 is affected, when you decrypt it, P1 will be wrong, but it will also XOR to this part, so P2 will also be wrong. This fixes the security problem of ECB. This means that if P1 and P2 are the same, C1 and C2 will be different, most probably, of course. Advantages, again, I mentioned parallelizable decryption, but the disadvantage is no parallelizable encryption, no random access, no easy way to jump ahead to later parts of encryption process. Another problem is that if ciphertext blocks are identical for some reason, for instance, if CI equals to CJ, then we have MI XOR MJ equals to CI minus 1 XOR CJ minus 1 due to birthday paradox. Such a case happens when this many blocks are encrypted. So if you are using CBC, after you encrypted this many blocks, and if B is small, this can happen in a short time. For instance, if B is 32 bits, your block size is 32 bits, then performing a small amount of encryption will mean that at some point you will obtain this kind of a collision. So depending on your block size, we might inform you to change your secret key from time to time, depending on how many blocks you encrypted. But of course, if B is large, like 128 bits, this means that you need to change your secret key after encrypting 2 to the 64 blocks. And 2 to the 64 blocks is a very huge number. Most probably you will never encrypt that many blocks, okay? But again, if B is small, and you will have this kind of collisions, and you might say that what is a problem here? The problem is that if this is equals, then you will know that XORing these two values will give me the XOR of these two plain text blocks. This doesn't actually leak MI or MJ, but you capture the XOR of MI and MJ. But since the plain text have some redundancy and so on, you might find some part or all of MI and MJ from here. So you should be careful when you are using CBC, okay? If your block cipher has a small block size, then you shouldn't use it, okay? Again, there is no self-synchronization. Let's move on to the third one, Cipher Feedback, CFB. Instead of a plain text block, encryption of an IV and its XOR with the plain text block are considered as the input in this mode. So here we are XORing we are encrypting XIs and then XORing them with MI, okay, where X1 is the IV, okay. So here I'm saying that CFB mode turns the block cipher into a stream cipher, and this will be more clear in the picture. So let's look at this. We start with IV. Instead of encrypting the plain text 0, I encrypt the IV, then XOR it with the plain text block and obtain C0, then take this C0, put it here and here and here. So as you can see, we added the plain text at the end as an XOR. Now the good thing is that the person who wants to decrypt will do the same thing, because they will start with the IV again. They will encrypt this IV with the secret key and obtain this value like here. So initially, the person also obtained this value and XORed it to the plain text, because the person who is starting the communication knows the plain text. But at this point, we don't know what the plain text is, but we have the ciphertext. So we XOR this value with the ciphertext. Since XOR operation is just addition modulo 2, changing the places of C0 and P0 gives you the different, just changes the positions of the result. So here you XOR it with C0 and obtain P0. Similarly, you do this. So as you can see now, encryption and decryption are almost identical. So I don't need to implement the decryption of this algorithm, right? Because both encryptor and the decryptor performs the same operation. The only change is that encrypting person XORs with plain text blocks and the decrypting person XORs with ciphertext blocks. So by stream cipher here, we are actually thinking this as follows. By performing these operations, we are actually here producing key stream, okay? Then XOR it with the plain text and obtain a ciphertext. This is why we call it that it works like a stream cipher. So actually from a block cipher, we kind of obtain a stream cipher here. We haven't seen the stream ciphers in detail yet, but this is the main idea behind the key stream generator, okay? So advantage is that error propagation is limited to 2 blocks. Disadvantage, non-parallelizable. a block can be encrypted if the previous blocks are encrypted. As you can see, I cannot encrypt P2 because I have to wait all of these serial operations, okay? So we don't have random access and no self-synchronization. So this only helped me in the way that I don't have to implement the decryption operations, okay? So let's do this in a better way. This actually lets us to move on to OFB, output feedback. Similar to CFB, but the input blocks are the outputs of the encryption, not its XOR with the plain text, okay? So again, here I mentioned that note that OFB mode turns the block cipher into stream cipher, thus IV and key should not be used twice. So in this mode of operations, IV always changes. So maybe instead of IV, we should say no, so that it will be more clear. But again, as I already mentioned, the literature sometimes uses the word IV, sometimes nonce. But in this scenario, I see it as a nonce, not an IV. But since people say IV, if you use the same IV twice, they will call it an IV reuse attack, okay? Let's look at the picture and then we will talk about what is the difference. So as you can see, it looks almost identical to CFP. So let me go back to CFP and see what is the difference. Here, you know, this line comes from after the XOR, okay? If you take this line and put it here, then you obtain OFB. That is the only difference, okay? Let's go to OFB. And this is how OFB works. You have the IV, you encrypt it with the secret key, obtain again some key stream values, and directly use it here, here, and here. So you may leave the XOR operation at the end. So this allows you actually first perform the encryption even when you don't have the plain text. So you can perform this encryption and, you know, store all of these key string values. And once you obtain the plain text, for instance, this might be your voice, this might be a voice communication. So once you start talking, you can simply XOR all of these values and provide the ciphertext without having any latency, okay? This is the good thing. So in the decryption, again, everything is identical, but we switch the places of P0 and C0. So you might now ask why using the same IV twice is a problem, because once you fix the IV and the secret key, the values you obtain here, which I call key stream, will be always the same. So you have a key stream here, you XOR it with your plain text and obtain the ciphertext. And when you're going to encrypt another plain text, you will again use the same key stream with the different plain text to obtain ciphertext. So this way, once you use the same IV twice and obtain two different ciphertexts, the person who XORs the ciphertext will get the XOR of your two plain texts, okay? This is the problem. This is an IV reuse attack, okay? This is why you shouldn't use IV twice here. This is again why I don't like the word IV here. I will prefer nonce instead of IV, okay? So if you use OFB, in every communication, you have to say what the IV is for that encryption, okay? But I will talk about it more when we talk about counter mode of operation, which is the next one, okay? Advantages: no error propagation. Erroneous bits in the ciphertext only affect the corresponding bits in the plain text. So this is a good thing. For instance, if only one bit of the ciphertext flips, during the decryption, that plain text bit will flip. So instead of losing whole block, you actually lose a single bit. This is a good thing. Encryption does not depend on previous ciphertext, since we just took this line from here to here. So we don't need to focus on the previous ciphertext blocks. Again, it doesn't provide synchronization and so on. Okay. Let's move on to the one that I like and which is the one that is used a lot. I will talk about it more in a minute. Counter mode encryption. Counter mode encrypts a chosen counter and XORs it with plain text block to obtain ciphertext block. The counter is incremented for each block. So instead of encrypting plain text, you choose a counter XI, you encrypt it and XOR it with your plain text to obtain the ciphertext. Then you increment this counter and continue in that way. Note that CTR mode again turns the block cipher into a stream cipher. Thus, the counter and key should not be used twice. And there was a ransomware, a Turkish ransomware, made this error. So this is why we like it. So I will briefly mention it here. So years ago, the initial Turkish version of the famous ransomware called CryptoLocker used AES in the counter mode to encrypt first 2 megabytes of your file. So for those people who doesn't know what a ransomware is, so malicious software kind of affects your computer, which we call ransomware. So most probably you click a link when you receive an email, generally saying that you have a cargo or something, okay, so or a plane ticket problem or something. So you click on it. So if your antivirus software doesn't detect it, the virus affects your computer as follows. It encrypts all of your files, but instead of encrypting the whole file, they encrypt the first 2 megabytes. And if you lose the first 2 megabytes of a file, then generally that file is useless. So it encrypts first 2 megabytes of your most important files, generally your files on the desktop or important folders and so on. Then on the screen, it says that they encrypted your files. Now they are asking you to pay ransom in cryptocurrencies. 90% of the time today, they ask for Bitcoins. 10% of the time, they ask for Monero. At the time when this first happened, they asked for 2 Bitcoins. And at that time, it costed like $600. But today, I think it is more than 40,000. So they, instead of asking for 2 Bitcoins, they asked like 0.3 Bitcoins or something. It depends on the current value. Okay. The problem was that they used the same counter for every file encryption. So this is something I accidentally observed. So this allowed me to actually recover all of the plaintext, because obtaining one unencrypted file allows us to decrypt every file, since XOR of the plaintext and the ciphertext provides the key string. Okay. So even if they used AES and a very good counter mode, a mode of operation which is counter mode, they just use the same nonce twice, same counter twice, and this way actually we could easily recover all of these files. And this is actually important because some Turkish people couldn't understand the problem here, and I listened to many talks where they say that counter mode is a very bad mode of operation due to this, because they think that it doesn't provide you any security, and anybody can decrypt any ciphertext that is encrypted in the counter mode. This is not correct. Counter mode is used a lot, and it is one of my favorite, and there's no problem with it as long as you know how to use it, okay? Never use the same counter twice for encrypting different files. That is the whole idea, okay? So it works like this. You have the counter, but generally counter is like 1. Okay, so for instance, if you choose your counter 1 and think about AES, you have 128 bits. So you start with a lot of zeros and then a 1. And some people think that, of course, in the next block, you will increment it with 1. So it will be 0, 0, 1, 0. And this 1, 0, 0, 0, and 1, 1, and so on. So they think that this might be a problem because, since it contains a lot of zeros, and also it will be hard to just keep track of all of the counters that you are using. So what they do is as follows. They create a 64-bit nonce, which is randomly generated at that time, then choose a counter and perform this operation. And in the next encryption, they choose a different nonce. So this way, if you even choose the same counter, the whole block will be different. So this way you actually get rid of this problem, okay? So as you can see, there are now no lines between here and here. It looks like ECB mode of operation, but instead of plain text block, I'm encrypting counters, sometimes with nonces, and then XOR it with the plain text. So the decryption is almost identical. I changed the places of PIs and CIs. So it is fantastic, and everything works fine, okay? Advantages: parallelizable. A block can be encrypted without waiting the encryption of other blocks. Random access. A block can be decrypted without waiting the decryption of other blocks. Error propagation is limited to a block. If a single bit of a block is flipped due to a transmission error, it does not affect other blocks. Encryption does not depend on previous ciphertext. And only disadvantage is that there is no self-synchronization, which we weren't expecting to have anyway. Okay, so this looks like the best scenario, and actually it is. Okay, so if you also want authentication, we will talk about GCM mode, Galois mode of operation, when we are going to talk about message authentications or authenticated encryption. We will talk about it, but without that, without authentication, this is the counter mode. So you might think that, you know, for every file, having a nonce or counter and, you know, saying this during the transmission might be hard to do, right? So some people think that this mode of operation never used, but actually it is used a lot. For instance, if you have an iPhone or a recent Android phone, it comes with a full disk encryption enabled as a default value. So in that case, they encrypt your files using this mode of operation. Of course, if it is GCM, they also produce a tag, but let's focus on this part. So assume that all of your files in your mobile phone encrypted in this mode of operation. So you might think that, then what are the counters for all of these files? So since you're actually writing your files on a disk, and disk is, you know, it can be 128 gigabytes and so on, but it is determined with blocks and sectors, right? So every part in your hard drive has a block number. So that block number actually is used as your counter. So this, since you cannot write this, two different files at the same part of your hard drive, they cannot have the same counter here because they cannot have the same block number. Okay, so this is the good thing. So this is actually what happens in the background in your mobile phones. Okay. Of course, if you are going to use it instead of a file encryption, if you are going to use this during the, for instance, voice communication and so on, so you have to initially tell what will be the nonce or the counter during this communication. Okay. Okay. Finally, let's talk about XTS mode briefly. So this stands for XOR encrypt XOR based tweaked codebook mode with ciphertext stealing. So it is a very long name, but idea is that it uses ciphertext stealing, so it doesn't cause any message expansion. So this is why it is used in disk encryption. So AES with XTS mode is a disk encryption standard since 2007 as IEEE standards. And from that time, since it became an IEEE standard, a lot of other standardization organizations also made it a standard. So for messages with lengths not divisible by B, the last two blocks are treated specially. That is the whole idea. Okay, by treated specially, we mean ciphertext stealing. Okay, so here's a picture. So, you know, it starts with your secret key. Generally, you can use two different keys. You perform the encryption here, obtain the value here. So you encrypt every plain text block, like here. Okay, and this operation is just like a small operation, sometimes a Galois field operation, but this changes the value here so that, you know, it is used like an IV here. Okay, I'm not going to go more in detail in this mode of operation. If you're interested, you can, you know, check the details. But again, it is used in generally in disk, full disk encryption. So if you go back a little bit and, you know, look at one of the pictures, as you can see, what I'm trying to do is that, you know, changing these places, these arrow places of these arrows, these XOR operations and so on. So you actually, you can do something more differently, right? Maybe you can XOR something here and then take this line here and so on. So you can do a lot of, you can generate more mode of operations if you want. And Philip Rajaway actually considered almost all of them. So if you're interested, you can find a free document on the internet called Evaluation of Some Block Cipher Modes of Operation. And there Philip-Rajaway actually looks at the advantages and disadvantages of almost every conceivable mode of operation that you can think of, right? Okay. And I already mentioned NIST documents, and I only mentioned the mode of operations included in these documents, but Philip-Rajaway actually considers more. Okay, if you need further reading, these documents might be useful. So let's finish this by looking at our examples. So let's recall the main problem that we started with this mode of operation process is that we didn't like ECB mode of operation, because I said that even if I use AES, which is currently like the best block cipher you have, I choose my secret key as 128 bits, which is secure. But because of choosing ECB mode of operation, it doesn't provide any security at all. So this was our main motivation, right? I told you that we shouldn't do this. So now I'm saying you that you can use counter mode of operation. So the question is, what would happen if I encrypted this image in the counter mode of operation? So this would the thing that you would see. Okay, it looks like a random noise. You cannot detect any pattern at all. But if you go back, as you can see, this is the original image, ECB mode of encryption and counter mode of encryption. So let's do the same thing with our different logos. This was our laboratories logo, CIDES. This was the ECB mode. Again, this is counter mode, full of noise. So anybody listening to the communication and capturing the ciphertext will see something like this. So this is actually important. So whenever you capture something, you should actually print it on the screen as like this, as a bitmap image. And if you see any pattern, then you will understand that there isn't any proper encryption here. Okay, because anything encrypted will look something like this. Okay, so this is a good way of starting at looking at, data you captured, let's say. Okay.